Thank you. Hello, thank you for coming. We are the Starspots team, and I am excited to share with you some of the work that we've been doing over the past couple months. I'm Daniel Giles. I'm a researcher. I'm joined by Tansu, Emmanuel, Lisette, and Stella. Our mentors have been Andres, Brett, Anna, and Siram, and we are so thankful for their mentorship and their guidance throughout the entire process. Let me begin by talking about the sun. The sun is central to our life on the Earth. It affects us every minute of every day. At its most extreme, it can take out satellites, it can take out power grids, leaving us in a state of chaos in just a matter of minutes. But on the other hand, it also sustains and nurtures life through its light and its warmth. And flares themselves may have helped in sparking life on Earth in the first place. For our neighbors like Mars, it stripped away all of those protections which are necessary for life, as we understand it on Earth at least. And understanding the stellar magnetic activity is key to understanding our stellar system. But understanding this magnetic activity requires careful observation. On the Earth, observing the sun, we can take detailed observations directly of the sun in a number of different ways. One of the most informative ways is to observe spots that appear directly visible to our eye. These spots are directly connected to the magnetic activity that's happening in the star. And by studying these spots, how they evolve, how they form, how they go through different activity cycles, we've come to our current understanding of stellar magnetic activity. But the sun is just one star of many billions of stars. Stars at different stages of their evolution, both younger and older than our sun, and which have their own planetary systems. If we can study the spots in even a fraction of these systems, we can gain a better understanding. We can glimpse the past and the future of our own sun. We can understand the habitability of other worlds, and we can understand the physics of our cosmos in a deeper way. I'll pass it to Tansu now to talk about some of the difficulties involved in this sort of study.
Thank you, Daniel. So space telescopes such as NASA's TESS and Kepler observe the brightnesses of thousands of stars over extended periods of time. And these one-dimensional time series are called light curves. And it is important to note that space telescopes do not spatially resolve the stars of interest here. In this context, our purpose is to use these data to infer stellar spots on thousands of stars other than our sun in our galaxy. This is a hard inference problem. It is mainly because a given light curve can be explained by many different combinations of spot multiplicities, locations, and sizes, as illustrated by the colored light curves here. And please do note that spots at different latitudes rotate at different velocities. Existence of more spots on the star just makes the problem even harder. And in addition to this degeneracy, the supervised learning or supervised machine learning problem is very challenging because there is very little ground truth information available. And given the large amount of data on these stars, the problem is inherently computationally expensive. Next, Emmanuel will talk about our methodology.
Thank you, Tansu. So we approach this problem from two different directions. For the first direction, we use a physics-based model, fully probabilistic. So we have prior distributions over stellar and spot parameters. And we try looking for posteriors from the real data, distributions over parameters that best describe the data. Now, doing inferences on this problem is difficult. So to combat this, we do a two-step solution. It's robust, where we combine state-of-the-art and traditional methods in order to get the best criteria possible. Even with scaling, inference can still be quite slow. So for the second direction, we also decide to go with a data-driven approach using supervised learning and using neural networks based on ground truth from real data. Not to reinvent the wheel, we decided to take state-of-the-art methods from well-known machine learning algorithms, and in order to facilitate this, we had to come up with different time series to image transformations that capture time correlations and distances and other features. And in doing this, we were able to regress single parameters given light curves. It's a neural network, so naturally it's much faster and much more scalable. So now we have this synergistic framework, which we call the Starry Spotter pipeline, which is the best of both worlds. You take the full Bayesian physical model, and then we take the fast scalable machine learning model, and together they cover each other's strengths and weaknesses so that we can get the best of both worlds. And now Lisette will explain the results of our efforts.
Thank you, Emmanuel. So here on the left, you can look at the excellent fit between our Monte Carlo model and the light curve data. And on the bottom, you can see how this probabilistic approach allows us to have a tight distribution of posteriors. That means that we can constrain stellar parameters such as the rotational period, the inclination of the star, and also the shear coefficient, which is key in differential rotation and understanding stellar magnetism. We can also find this distribution of parameters for spots themselves, such as their sizes and their location on the surface of the star. This method is quite compute intensive, so we can apply it to a few stars for now. And this is why we rely on supervised learning to tackle the data in a different way. So in supervised learning, we're taking advantage of this transformation of the time series into images in order to apply our convolutional neural network to thousands of stars. On the left, you can see how highly correlated our predictions for the rotation period for thousands of stars are to the ground truth, which is a previous study on these same stars. We hope to scale this up to many more stars in the future. And now for some final thoughts, here is Estela.
Thank you, Lisette. So we know light curves are highly degenerate, and before we used to have a very scarce ground truth, because obtaining ground truth is usually very computationally and observationally expensive. But now we have our Starspots pipeline, and with the probabilistic forward model approach, we were able to work not only with the rotation period of a star, but with the other parameters that describe star spots. We were also able to constrain the physical parameters, generating a currently growing ground truth dataset. Moreover, with our supervised learning approach, we were able to speed up the process. So we have now a pipeline, we have laid down all the foundation, and we are ready to get deeper in Starspot studies in a scalable way. So our take-home message is we are the Starspot team, and we want to understand starspots, and we have a big challenge. Disentangling signature of a spot from the light curve of a star. In only 8 weeks, we combine different models to constrain spots and stellar parameters on thousands of stars. Our next steps are to evaluate the uncertainty of our methods and apply them to many more stars, contributing meaningfully to the studies of stellar magnetism. So thank you, and a special thanks to all of our partners and external advisors.
Great. Thank you so much, Starspots. That was really wonderful. And I'm going to invite our panel back up. So this time I'd like our panel to either give one word or one sentence about what does this work with their Starry Spotter and the work they've accomplished make possible. And to kick us off, please, Scott, you're up.
I would simply say scalable star spots for the win in astrophysics.
Thank you, Scott. And Aaron?
Yeah, just kind of the obvious physical and rotational understanding.
Thanks. And Rodney?
So one word, transformational. The fact that you're faced with a lot of challenging circumstances and you could transform them into actionable information that actually is explainable and accessible to a broad, diverse set of folks is, I think, pretty impressive.
Great. Thank you, Rodney. And thank you to our panel and to our Starspots team. To close out our heliophysics section, I'd like to wrap up with a video from Google Cloud that highlights the work of the previous FDL. So if we can please play that video.